Okay, hello class. So we had finished up last time talking about how to estimate the work done by looking at a vector field, and now this lesson is about computing it precisely. And so this is a vector field, f of xy equals 1, 1. So a nice, easy, constant one to plot that I could do by hand. And we are on the page computing work integrals in your journals here. And that's the field I copied onto the board. And we have this path in red from a point A to a point B. And from the last lesson, we were able to say, okay, well, moving along this path that we can see that in general, we are moving with the field. So the field's work is positive. And we want to quantify that and be able to give a precise answer. How positive is it? Is it 7? Is it 11? Okay, so to do that, we want to come up with a derivation for a formula for work. And we're going to do it with something called a work integral. Okay, and so the idea is something that we've done repeatedly. And this is actually our last time to do this approximate, refine, limit idea. But at any point we talked about to estimate the work, we were saying, are you moving mostly with the field? And you could stop along your red curve, which that is your space curve. I'm sorry, your plane curve, R of t. And so that has components x of t, y of t. And you could stop and say, maybe for, remember our plane curve is parameterized by t. So that's the thing that we could make small increments in t. And so maybe for a small unit length in t, I get to the next point and maybe another small amount of t. Sometimes maybe it speeds up along that curve. So it might be here and then there. So they're not going to be necessarily uniformly spaced because t is uniformly spaced, but where it appears on R of t may not be. But at any rate, what you would do is check the direction of the space curve. So r prime of t, its tangent vector. So at the initial point right here, its tangent vector looks maybe something like this. You'd stop and draw a tangent vector, and you'd compare that tangent vector to the red tangent vector to the black vector in the field. And you check the angle. And again, this angle, they're moving mostly in the same direction, so that's positive. And I'd stop at the next point, get its tangent vector, compare that with the black vector in the field, which is always constant, which is 1, 1. So we'd have one right there. We'd have another black one right here. And we just keep doing this at all these increments, looking at the black and the red, the black and the red, at all these points along the curve. And of course, if we could, we would sum those. So maybe we decide to do this for delta t for 20 delta t's along this red curve from A to B, and we'd keep getting the angle between the black and the red, which is done with the dot product. So we'd be looking at f of xy at that point for that particular value of t, dotted with r of t, or sorry, r prime of t. All right, so we would put a prime. And then we'd sum those. And again, if we were doing that for 20 of them, we'd sum it across 20 of them. If we did that for delta t in units of 100 delta t's, so divide this from A to B in t units of slamming 100 in there, of course, we're going to get a better approximation. And then what happens if we make that delta t go to 0, which is making the number of segments that we're doing go to infinity, which is the same thing as doing a definite integral, right? So we approximate, we refine that approximation all the way to the point of the limit, which makes that approximation turn exact, which is the formula at the top of the next page here for our work integral for an R2 vector field. So I'm going to go ahead and put that on the board. Okay, so here is our formula for the work done by an R2 vector field. And so we can have a similar formula for an R3, we'll get there. For now, we're going to look at this example, which is an R2 field, has a plane curve through it. And so if you want to measure the work done to move a particle along a plane curve R of t, so two-dimensional, over the domain from T goes from A to B. So that was like our picture before with our vector field. This is your work. So you're doing just exactly what we said. We are summing, if you did it with the Riemann sum, do it to delta T goes to 0, or the number of segments that you're doing goes to infinity. You actually get this definite integral, but you're dot producting the tangent vector along that plane curve with the vector in the field at that point. And so we are going to take F, evaluate it at, we have to turn that originally is given in X and Y, so we have to somehow put that into T. So we're going to take, evaluate that at X of T, Y of T, and over the limits from A to B. That makes sense. And remember, this is your dt takes small increments in the time, the parameter for the plane curve. That's like your delta t, but when you take this to the limit, you get dt. Okay, so all this formula makes sense, nothing to memorize. You just think about what you're trying to do for that vector field. And so now we want to look at the next example. And this is an example where there is a vector field in R2 that represents wind, the motion of the wind. And then there's a sprinter that's running along this path doing a 100-meter dash, trying to break her record. And the question is, what help, if any, does the field, the wind, provide her in her, does it give her a boost? Is it a tailwind mostly? Is it headwind mostly? And then precisely how much? So maybe you want to quantify that if it is a record, but you're knowing that it has a tailwind, you get a little asterisk in the record book next to that. So let's take a look at what these look like visually. So we'll go to the tech tool, CalcPlot 3D. And I've already entered these in. So our R2 vector field is given here. We have an M and an N. The P is 0 because we're R2. We restricted it to R2 view. Those are the blue vectors that are plotted with the constant primary color chosen here. There's kind of a lot, or they're kind of long, so maybe we want to shrink them a little bit. Divide by 6, maybe even more, divide by 8. Okay, so again, that's showing that the wind's kind of swirling, but the sprinter's motion from time 0, so that this is the plane curve. We set z to 0 because we only have 2 components. We make sure t is over its domain of 0 to 1. Let's add a few orientation errors. So we see that she's starting down here is the start of the race. The finish 100-meter dash is here. And for the most part, she has some tailwind. I mean, it's helping. It's sort of, not quite orthogonal there. And then it's starting to sort of direct her. She has a bit of a tailwind. So the wind is helping her. And now we want to quantify that. So that's what we visually see. And now we have this nice formula that's going to help us quantify. And really, we're just summing up. We're really doing a Riemann sum to infinity. And so to apply this formula, then we're trying to get the work will be the integral. T is our parameter, 0 to 1. So this is going to be dt's. We are going to dot product the vector field. And we'll make some space here with the derivative. So move that here, put the derivative right below. R prime of t is going to be 0, 4. So 0, 4 back here, that's easy, a nice constant. But what goes in front here, that's our R prime. And this was 0 less than equal to t less than equal to 1. And then what goes in front here is f of x, t, y, t. And right now, f is given in terms of x and y. So we need to now write this in terms of our plane curve. The first component is x of t. The second component is y of t. So we need to figure out then, maybe before I add a step here, we need to figure out what the vector field capital F at 5/3 minus 2 plus 4t is. All right, now we'll evaluate this. The vector function says the first component x is 5/3. You're going to take that and multiply it by 2. subtract 3 times the second component. So we will then get the vector. 2 times 5/3 is 10/3, minus 3 times this next component. So that'll be minus 3 times minus 2 plus 4t. And then the second component says you take your 4x minus 2y becomes 4 times 5/3, which is 20/3, minus 2 times minus 2 plus 4t. And then we'll dot that with 0, 4. So just some arithmetic and cleaning up this one before we do the dot product. So let's see, 10/3 plus 6, that'd be 18/3, so 28/3 minus 12t. That's our first component. Yeah, that looks right. And then 20/3 plus 4, so that'd be 32/3 minus 8t. Dot that with r prime, which is just the constant vector. Okay, so now we're ready to do the dot product. The first one, 0 is nice, so that term goes away. The second one, we just need 4 times the 32/3. Still haven't even done the integration yet, so from 0 to 1, I'm carrying that along. Let's see, what is that? 128/3. Minus 12t. dt. Okay, so no problem on that integration then. Finish this up. So integrating with respect to t, so 128/3 t minus 12t squared over 2, so minus 6t squared from 0 to 1. So we just have to plug in at the upper limit because the 0 goes away. So 128/3 minus 6. So that's 18/3. 110/3. Oh wait, I see something right here. I think I made an arithmetic error right here. Yeah, so I did, when I do the dot product of these two vectors, the first terms go away. So I just need 4 times this, and I did that correct. Minus 4 times 8, I don't know why I added that. So that should be 32. So that'll be 32t squared divided by 2. So what is that? 16 t's minus 16. So now I need to subtract 16 times 3 is 48. Is that 80? Does it look better? Okay. Right, so what we see now is we have quantified. We knew from the image picture of this that we expected positive work, but we want to quantify that. We now have this new formula. We were able to quantify exactly how much work that the wind helped this sprinter in 80/3 was the amount of help it got, that she got from the vector field. Okay, then we mentioned that this formula is for an R2 vector field. Oh, I should also say the other thing is that the space curve R of t has to be smooth. Why do you think it has to be smooth? Well, first of all, what does smooth mean? There are no sharp corners, cusp, holes, jumps, breaks. So this would be not smooth, it would be piecewise smooth on two pieces. We want it to be smooth. If it's piecewise smooth, you can sum up over the multiple pieces. We want it to be smooth or piecewise smooth because that means your derivatives exist at all those points when you're summing, right? So right here, these are problem points. We can sail off in two different directions, whether we're riding forward or backward with our tangent. So we need those R primes to exist and make sense. Okay, but this was again restricted to R2. Well, something exists for R3. What do you think happens? You now have, if we change this to R3, you now have a third component Z. So we have a Z of T. But we'd still dot that with R of T. So the formula, and of course this would hold for higher dimensions as well. So work formula for an R3 vector field is shown here, but you could do this for Rn. There's a nice example on that page to follow as well. It'd be a good one to put in a tech tool and visualize too, but it's the work done by a tornado to move an object along a particular path. Same idea, but just extends. You can imagine though that ours was pretty basic vector field in R2, nice linear path. You can imagine that as you complicate things and you have more interesting nonlinear ones, that your integrals get messier. Okay, I want to do one more problem, so I'll erase the board here. Okay, let's work another example. Computing work intervals. This is one of the main computations that you're going to do in chapter 3. So we have another R2 vector field. So we're going to use the simplified one where we don't have the Z component. We have this plane curve. We want to compute precisely the work done by the R2 field to move the particle along this path from 0 to 1 for T. So let's visualize this. We don't need to do that to do the computation, but let's just take a look. It's always a good idea. Back to tech tool, CalPlot3D. Change our function to our vector field is x cubed minus y cubed in the first component, and then xy squared. An R2 field, let's see, so what's happening? We're kind of circular motion that's expanding and going out. And then our plane curve is 2t squared, 2t cubed. T is also from 0 to 1. So the red curve, this section here. And again, we're wondering, is the work, it'd be a good idea just to get an estimate. Is it going to be positive, negative? An idea of that happening here. Maybe we should add a few more, a little more. Okay, so maybe sort of orthogonal in the beginning there, moving with it, with it, with it, with it, with it. Okay, so we'd expect a positive value when we do this computation. Okay, so let's go ahead and crank away on the computation. The formula is we need, our goal is to think about that red plane curve. How much does it coincide with the field? So we're looking at these two vectors, the tangent vector r prime of t that moves like the red plane curve, and then the black vector that was in the field. So we want to take work, so nothing to memorize. If you just think about what's happening here, we want to dot the field, but we need to turn it into dimensions with t, because this is going to be a dt. Dotting it with that tangent vector, the red tangent vector, and then the black vector in the vector field. Okay, so we can do a little computation here. We need a derivative. R prime of t is going to be 4t 6t squared. So that's going to go right here. But then we need to do a little work at the beginning here to figure out what x of t, y of t is. So again, remember That's the definition of your plane curve. And so we need to figure out f at 2t squared 2t cubed. And then we'll dot that with this derivative vector. Okay, so f 2t squared 2t cubed. So what I do is take that first component and cube it minus the second component cubed. So let's see. Cubing this would be what? 8t to the 6th minus cubing this one would be another 8, but t to the 9th. And then the second component, I multiply 2t squared times this component squared. So that's going to be 2t squared times 4t to the 6th. And let's go ahead and just write it out in room down here. That is 8t to the 8th. I need to dot that with this tangent vector. So let's see, this times this plus this times this. So we'll have 32t to the 7th minus 32t to the 10th plus 48t to the 10th, which is 32t to the 7th plus 16t to the 10th. dt. All right, now we're ready to do the integration. Let's see, can you see? Yeah, there's a little more room over here. So we go ahead and do the integration. We'll have 32t to the 8th over 8, which is 4t to the 8th, plus 160t to the 11th over 11, from 0 to 1. What is that? 4 plus 160 over 11, which is getting a common denominator, 44, 204 over 11. Okay, which again fits because we expected a positive value, maybe a large positive. There's quite a few that the field was moving. The curve was moving with the field. Yes. Okay, so now that we can compute work integrals, we're going to do that over a couple different fields and then come back and connect it to gradient fields, which we're also going to call conservative fields. So that's the next topic.